Hi, I'm Professor Seth Chandler at the University of Houston Law Center, and this is a video on Bayesian statistics, part of a series of videos for the course Analytic Methods for Lawyers. There are times when what appears to be a minor discovery by an obscure person changes the world, and such is the case with the work of the otherwise unheralded 18th century cleric, who in a book not published until after his death developed both a philosophy of statistics and a little equation, both of which have changed the world. His work split the world of statistics into two almost religious camps, now known as the Frequentists and the Bayesians. Most of what has been taught in this course is Frequentist statistics. I do that because that branch of statistics is valuable, and perhaps more importantly, because it is still the majority religion and it is accepted in court. But the Bayesian camp is growing, perhaps because the computations it requires were, for many years, far too difficult to be performed on any mass basis or with any complex data. With the advent of modern computers, however, the ideas of Thomas Bayes, reached 2.5 centuries ago, now thrive. And this essay is about both those ideas and a recent rediscovery of a concept that makes their meaning more intuitive. Let me start with a story that grows out of 2020, the year in which this essay is written. Suppose you've been advised that of those infected with COVID-19, a given test will so indicate 90% of the time, and of those not infected with COVID-19, that same test will so indicate 95% of the time. It would appear to be, in other words, a pretty good test. And now here's what happens. You take a COVID test, and it comes back positive. What's the probability you actually have a COVID-19 infection? Let's get rid of the easy wrong answer first. An answer of 90% is completely and totally wrong. And one way of seeing why is to realize that the statistics you already have ask the wrong question. They ask, given that you have COVID-19, what's the probability the test will say so? But that's the opposite of the question that interests you. You want to know the reverse. Given that the test says you have COVID-19, what's the probability you really have it? Now, you might think that's an impossible question to answer. But what the Reverend Bayes tells us is that the question is not impossible at all. It is an extremely calculable number provided. And the proviso is, you must have some prior belief about the incidence of COVID infections in people like you. Suppose that in the group of people you believe similar to yourself, the rate of COVID infection at the time you're tested is 2%. It's present, it's serious, but it's just not all that common. So let's make a matrix of people. The rows will describe whether the person really is infected with COVID, and the columns will describe their performance on the test. The only constraints are that the rows must have 98 people in the no COVID row for every 2 people in the COVID row, because that incidence is 2%. And in the COVID row, the fraction of people in the test positive column must be 90%. And in the non-COVID row, the fraction of people in the test negative column must be 95%. Okay, let's build a categorical distribution that reflects those numbers. You'll notice I'm using some multiplication here, and we now have our categorical distribution describing one category is really no COVID or really COVID, and then the other category is whether my test result is negative or positive. So what we want to do is to look at the joint probability of the disease and the test result. And to do this, I could just go like this, but I think we'll do it programmatically, and we'll ask for information about the categorical distribution. We'll ask for the probability distribution. All right, and there it is. Those, if you add up all those numbers, they will add to 1, and that's how people are jointly distributed among either having COVID, no COVID, having COVID, and then whether their test result is going to be negative or positive. Now we can do the computation. First, I'm going to do it the Wolframy way. Let's take a look at the distribution of disease states conditional on the test being positive. So I'm going to form a conditional categorical distribution, and the condition is that the second category, negative or positive, takes on the value of positive. What distribution is this being based on? It's being based on CD. That's the symbol that I assigned the categorical distribution to. So we're going to compute that and call it CCD. It's going to take a moment because it's got to go out to the web and get the conditional categorical distribution resource function. Come on, interweb. There we go. So we now have a distribution. You'll notice this has only one dimension of categories. Now it's the question of, do you have COVID or do you not have COVID? And now, again, let's use information on this conditional categorical distribution to get the probability that you actually have COVID. And as it turns out, although the test is pretty good, and the test unfortunately came out positive, it's much more likely that I do not have COVID. Okay? So, this is often a counterintuitive result. When various doctors are given these sorts of problems and asked to estimate things, they always get it wrong, or not always, many of them get it wrong. And this is why Bayes' law is in some sense so important, is it helps answer questions like this. Now, what do you do with this information? That's a whole complicated story that may be outside the scope of this course, but at least you know what the answer is. All right, so I did it very Wolframy here. Let's see if we can just sort of do it by hand. Let's look at this. Okay, here's our distribution, and we know that we're only looking at people here, right? Only people who are positive. So what's the fraction of people that who are positive that have COVID? It's 0.018, so that's going to be our numerator. And our denominator is going to be all the people who were positive. So that's 0.018 plus 0.049. And if we do that, we get that 0.268657 number that is what we saw down here. So in this instance, it's not that hard. We can do it by hand. And in fact, it really, if you get used to forming these matrices here, it's not very hard to do it by hand. You just have to kind of keep track of what your categories are. All right. What we just did is called a Bayesian updating of probabilities. Before we took that test, we were like everybody else who was like ourselves. There was a 2% probability that we had COVID. And so before the test, the distribution of COVIDity, if you like, was a Bernoulli distribution. You remember that's the coin flip, except that we have a parameter which specifies the fraction of heads. And the parameter was 0.02. After the test, our posterior probability was 0.269, which represents a Bernoulli distribution with a parameter of 0.0. No, that's not right. A parameter of 0.269. So the test updated our prior distribution into a posterior distribution. As it happens here, the distributions are both members of the same distribution family, Bernoulli distributions. That's not always the case, but it is the case here. Sometimes it's pedagogically best just to start out with a concrete example, and that's what I did there. But let's actually see if we can derive Bayes' theorem. So, same idea here, which is we've got people who actually don't have COVID and people who do have COVID, and then we have people who test negative and people who test positive. Let's fill in the values of that categorical distribution, and let's assume that a fraction A actually have COVID, and that a fraction of those who do have COVID, a fraction S test positive, and of those who don't have COVID, a fraction C test positive, okay? And obviously, if A do have COVID, then 1 minus A don't have COVID. And if a fraction S of those who do have COVID test positive, then 1 minus S of them must test negative. And the same thing here. If of those who don't have COVID, if C of them are positive, a fraction C of them are positive, then 1 minus C of them must be negative. So now let's actually form our categorical distribution. We did it. And let's derive two distributions from this joint probability distribution. I want to derive a conditional categorical distribution, and I'm going to do it exactly the same way I did before. I'm going to say the condition is that the value of the second category must be positive. So we do that. And I also want to look at the marginal distribution of testing. So that's the second marginal. Done. All right. Now let's look at the probability table for each of these two distributions that I just made, the conditional categorical distribution and the marginal distribution. And the only thing I'm going to do here is I want the expressions to come out in a simplified way, so I'm just going to map simplify or full simplify over each of them. There is our probabilities for the conditional categorical distribution. I know it looks a little complicated, but just wait. And there is the result for the marginal distribution. Ready? Watch this. Let's look very carefully at this table. In fact, I'm going to blow it up here a little bit. Let's magnify our screen up to 200. Okay. Let's look at this carefully. It's a fraction. What's the numerator? The numerator is A times S. What's A? A was our prior. A was the probability that the average person had COVID. What's S? S was the probability that if you had COVID, you would test positive. Okay? So that is our numerator here. Now, let's look at our denominator. It's not instantly obvious what that is, but if we go down here, that's the same expression as here. That's the total number of people testing positive. And so, what we have is we now understand that this is the prior multiplied by a conditional probability, all divided by a particular marginal probability. And so we can now see Bayes' law. The probability of A being sick, having COVID, given that you tested positive, is the probability of the average person having COVID, that's A, multiplied by a conditional probability, the probability that you would test positive if you had COVID, that's our S, divided by the probability that you had COVID. That's this thing right here. And so, although the notation was a little bit different, what we just did was to prove Bayes' theorem. And as I write, that is a big, big deal. It's one of those things that after you've seen it, it seems kind of obvious. It almost seems trivial. Trust me, it is anything but trivial, and you should be able to understand the rudiments of this proof. Okay? You should be able to understand why Bayes' law turns out the way that it does. Now, let me show you an alternative way of deriving Bayes' law. And it's not only a way of deriving it, it's really a way of doing computations with Bayes' law. that I think is actually a lot easier. And this is purely the work of a guy named Grant Sanderson. He runs a YouTube channel called 3 Blue 1 Brown that has a lot of subscribers for good reason. And he recently presented this alternative way of thinking about Bayes' law and Bayesian updating. The central insight is that Bayes' law updates odds. And the key step is to think about odds rather than probabilities. So, if the probability of some event is p, the odds are p divided by 1 minus p. It's just a different way of expressing the same concept. So, if you've got a horse and the probability of the horse winning the race is 0.25, the odds are 1/3, often written as 1-3, or 3-1 if you're focusing on the odds against winning. Okay? If the probability of having COVID-19 before any tests conducted are 0.02, the odds are 1-49. Probabilities are bounded between 0 and 1. Odds are bounded between 0 and infinity. And that's the lovely part, because if it's bounded between 0 and 1, you can't just multiply things by probabilities, because sooner or later you might get something bigger than 1. But odds are bounded between 0 and infinity, which means you can multiply odds by any positive number and still get something that is potentially an odds. That is, odds are in some sense closed over multiplication. So here's a trivia. I just wrote down the formula in Wolfram language notation, and we can do a little algebra and figure out how to recover the odds of probability from the odds. Okay, ready for this? I think we've seen this diagram before. It's a confusion matrix, a lovely name. And there are two conventions about what goes on the rows and what goes on the columns. It's like the yooks and the zooks from the butter battle. They're equally valid, but we have to pick one convention. And I'm going butter side up, which is, I'm going to put reality on the rows here. So we've got whether someone's actually negative or actually positive here. And this is the test result, whether they're predicted to be negative or predicted to be positive. The sensitivity of that test is the true positive rate divided by the sum of being actually positive. It's what fraction of those who are actually positive test positive. The specificity of a test is defined as the true negatives divided by all of those who are actually negative. And the false positive rate is 1 minus the specificity. It's similar to type 2 error. It is the fraction of people that you predicted would be positive, but in fact are negative. Let me say that again, that wasn't so great. Of those who are actually negative, what fraction will you predict to be positive? So we're going to compute a ratio now. And that ratio is the ratio of the sensitivity of the test to the false positive rate. Okay? So what is that here? Here our sensitivity was 90%, and our specificity was 95%. And that means the false positive rate is 1 minus the specificity, or 5%. And so 90 divided by 5 is 18. That's our updating ratio. Okay? And so here's all we have to do. Whatever the odds were before, 1-49, the odds now are 18 times greater. We just multiply our prior odds by an updating factor. And so the new odds are 18 to 49. And I wonder what probability that is. Let's use that little function, prob from odds. And look at that number, 0.268657. Where have we seen that before? And we saw that before right up here. That was the same result we got before. But the beauty of this method is we simply look at the prior. That gives us our prior odds. And we update the odds simply by using a ratio. And then it's just a matter of multiplication. We don't have to do the somewhat complicated Bayes formula. Everything's very clean. We have one number, the odds, the prior odds, and we have another number that you just derived from the test information. That has to do with the ratio of the sensitivity to the false positive rate. And then you just multiply the two together. Isn't that nice? What if we got a negative result? It's really the same thing. We're going to update the odds. The only thing that's different is the Bayes factor is kind of reversed. What we're going to do is we're going to form a ratio, and the ratio now is the false negative rate, which is 1 minus the sensitivity of the test, divided by the specificity of the test. So since our sensitivity was 90%, the false negative rate has to be 10%, and our specificity was 95%. So our update factor is 0.1 divided by 0.95. So what were our odds before? Let's just see. Our probability was 0.2. So we're going to update that by 0.1 divided by 0.95. And those are our new odds, not our probability. And so we're just going to say prob from odds if we like working in probability space. And so the new probability, if I get a negative COVID result, I'm real happy. Probability I have COVID is 0.00214, etc. But there's more. One of the virtues of using this odds method is that if you have a succession of tests, you can just multiply their Bayes factor. So let's suppose you got this positive result, and now you want to take a second test to see if you can get some additional information. Assume the second test results are uncorrelated with anything on the first test. They're both correlated with COVID, but there's no direct correlation between the first and second test. Second test isn't so good. That's why they didn't give it to you the first time. Its sensitivity is 80% and its specificity is 60%. What happens if you test positive on that too? Well, what's the Bayes factor for the test? The Bayes factor is the sensitivity, 8.8, divided by 1 minus the specificity, 100 minus 60. And so that's 80 divided by 40, which is 2, or 0.8 divided by 0.4, which is still 2. So if that test comes back positive, the odds are now the old odds, 18/49ths, times 2, which is 36/49ths. And if you use the little prob from odds converter, 42.3%. So getting the second positive result, you're now no longer in the 26 point something percent. Now it's looking kind of gloomy, 42.3%. But what if the test came back negative? Well, now we just apply the negative update rule. What's the negative update? Well, let's see. The numerator is the false positive rate. That's 1 minus the sensitivity, which is 100 minus 80, or 1 minus 0.8. We divide it by the specificity, that's 0.6. And that's, if you do the little math out, that's 1/3. So the new odds are the old odds times this Bayes factor of 1/3, which is 6/49ths. And if you use that prob from odds thing, your new probability is 11% as a result of the negative second test. Isn't that cool? I think so. You remember how statistical testing worked back in the old frequentist world? You see some data, and you have to form a null hypothesis. And then you form the distribution of some statistic if the null hypothesis were true. And then you compute the same statistic for your own data. And 3, you ask how likely is it that you would see a value for that statistic as extreme as the one you do if the null hypothesis were true. But where the heck did the null hypothesis come from? And is item 3 an interesting question? Really, isn't what you want to know the probability distribution of a statistic given the data that you've seen? And that is what Bayesian statistics lets you do. So, here's an example. Supposing we see the following 7 items of data, and we're certain it comes from some Bernoulli distribution, but we have no idea what the parameter of the distribution is. It could be anywhere from 0 to 1, and we believe all of those values are equally probable. By the way, in the Bayes world, that's called an uninformative prior. You know what a Bernoulli distribution is by now. So let's look at here's our data. And let's find for an arbitrary Bernoulli distribution what the PDF of each outcome is, and then take the product of those PDFs. Okay? So we're going to get the PDFs of all the values, and we'll multiply it out to get the joint likelihood. And this works a lot better if you actually evaluate RVB. All right, so we get a polynomial in P. We can plot that polynomial. It looks like that. And kind of looks like a probability distribution, but if we find the area under this curve, remember for a continuous probability distribution, the area under the PDF should sum to 1. You're going to find that it's not 1. And you can either do the calculus if you like, or really you can remember what the rule is for triangles. The area of it's kind of a triangle, and the area of a triangle is 1/2 base times height. So here's the base 1, and here's the height 0.015, and then we have to divide that by 2. We're not even close. So although it kind of looks like a PDF, it's not quite a PDF. By the way, if you want to do the calculus, here it is. But supposing we take each of these values here and we divide them by 1/168th, or alternatively, we multiply it by 168. In that case, we will in fact have a probability distribution. So here it is. We're just taking our joint likelihood that we computed up here and normalizing that joint likelihood by dividing it by the area under the joint likelihood. And now we have an expression, and that is a probability distribution, or it's the PDF of a probability distribution, and that is the posterior distribution. That is the probability of that's the PDF of the distribution of possible parameters to the underlying Bernoulli distribution. So in the work we just did, we just didn't assume anything about the parameter. That is, we basically assumed that it had to be somewhere between 0 and 1, but we had no reason to believe it was more likely that it was 0.8 than it was 0.2. So we had an uninformative prior. And you could think of that as simply being that the distribution of the prior was the uniform distribution on 0, 1. But now let's assume instead that we do have a prior belief, an informed belief about the parameters of the Bernoulli distribution, and it's represented by a member of the beta distribution 7, 3. So just to be clear, this is the distribution of the parameter P to the Bernoulli distribution from which these numbers came out of the factory. We're not sure what parameter P was used, but we have some suspicion for some reason that it's distributed in this fashion, beta 7, 3. So we can plot that, a PDF, and there it is. Now, let's weight our joint likelihood that we computed above by the prior belief likelihood. And in terms of that formula we had, our joint likelihood is the probability of B given A in our Bayes formula, and our prior distribution is the P of A in that formula. So basically what we want to do is calculate the numerator of that Bayes law fraction. So we're going to just compute it here. Joint likelihood times the PDF of the beta distribution, and I'm just going to add a little refinement here to remind Wolfram that P has to lie between 0 and 1. Okay, so we do that, and we get a slightly different polynomial than we did the other time. And now again, what we need to do, if I integrate this expression, and I take the all caps lock key off, And remember, percent means the last thing you saw. I think I've talked about that. We'll integrate it from p goes to 0 to 1. We're going to see that that is not, again, 1. So in order to turn this into a probability distribution, we have to normalize it, and the way we normalize it is by dividing it, each element, each weighted joint likelihood, by this integral here. Okay? So let's do that. And now we get a different number. It's the same here. It's just that there's a different coefficient in front of it. And so now I will turn that into a probability distribution object by wrapping probability distribution in front of it. And the second argument is the domain of the probability distribution. This is the PDF, and this is the domain. So there we go. And now what we want to do is to compare the posterior PDF when we make the least restrictive assumptions about the distribution of P, uniform distribution on 0, 1, and when we make more restrictive assumptions about P. That is, that we thought it was distributed a beta distribution 7, 3. By the way, the least restrictive assumptions is sometimes called the maximum entropy distribution. And if you don't know anything, you should probably be using the maximum entropy distribution. But you don't have to know in this class how to actually find the maximum entropy distribution. All right. And so there we are. So the blue line represents our estimate of the parameter to the Bernoulli distribution when we made no assumptions, maximum entropy, about the distribution of P. However, if we had some prior information, it's moved. You see how the gold line here, it is different than our original beliefs that we put here. That is, we've shifted leftward somewhat in light of the fact that when we go look at our data, there are a lot of zeros here, and that's kind of inconsistent with having a high P parameter to the Bernoulli distribution, but we haven't gone so far as to just look at that data. So I hope that shows the role of the prior in conducting Bayesian estimates. And this is sort of the virtue and vice of Bayesian statistics. You get very useful information out of the process, but the information you get depends on your initial assumptions. And so if you see a distribution that's the result of Bayesian reasoning or a statistic derived from Bayesian reasoning, you need to start getting more information about what prior was used, why it was used, and try and find out how the result might change if a different prior were used. So for example, supposing, remember that example about COVID, I said the incidence among people like me was 2%, but what does like me really mean? Maybe among people who thought a test was warranted, actually, the incidence is 4%. Why do they need a test? Because they were out at a bar last night or whatever. So figuring out what prior to use is extremely important to Bayesian reasoning. Bayes' law is incredibly powerful, and its conclusions are really interesting, but they are also sensitive to the prior that's selected. Let's now turn our attention to something called the credible interval. In traditional frequentist statistics, we often calculate whether a particular statistic is outside the interval we would expect to see if the null hypothesis were true. You remember that's what we've been doing all along. We basically, either mathematically or through simulation, figure out what the distribution of some statistic would be if the null hypothesis were true, and we see whether the statistic that we have is particularly unlikely under that distribution. And the interval that we might select for where our statistic is not so unusual that we're going to say that the null hypothesis is disproved. That's called a confidence interval. A Bayesian, however, they don't have this null hypothesis business. Thank goodness. Instead, they use something called a credible interval. Now, they could have picked a better name, in my humble opinion, because they both start with CI, which is annoying, but that's the world we live in. So let's actually use some algebra and see if we can find the values x1 and x2 such that 95% of the posterior distribution lies between them. We could then say that given the data that we have and our prior beliefs about the distribution of some parameter or other, in light of the data, we are 95% certain that the value of that underlying parameter lies between whatever, 0.3 and 0.8. Okay? So let's use some algebra to do this. Remember that we're going to be using the posterior dist-weighted symbol here. What is that thing? That's the probability distribution we computed when we had a prior about the data, about the parameter, beta distribution 7.3, and we were going to update that prior according to the data that we observed. Okay? So let's go back now, and this is just a little bit of kind of icky algebra, but what we want to say is we want to find where the difference between the CDF of the posterior distribution weighted, evaluated at x2, minus the CDF of the posterior distribution weighted at x1 is 19/20. The rest of this is just to help Wolfram research, or help Mr. Wolfram out in doing the computation. And I'm going to make this a function of x1. Why is that? It's because there are multiple such intervals, right? I could wiggle the bottom value, and if I move the bottom value to the right, then the top value is going to move to the right. Let me say the following. This might be the most complex piece of code and conceptually the most complicated thing we've done in the course so far. And so it's a good opportunity to test your understanding, because it's going to require you to understand what a CDF is, understand what this posterior distribution weighted thing is, and then there's a little bit of coding here. All right, so we are going to ignore that little warning. And by the way, if I now evaluate that, let's do it. Credible interval upper bound, and I'm going to say, supposing I think the lower bound is 0.04, it's going to return, well, then we're 95% certain that the upper bound is 0.72. Okay? If, on the other hand, I thought the lower bound was 0.09, it would say, well, then I think the upper bound is it's a little higher. What if I think the upper bound is 0.23? We keep moving up. Should I do, I don't know if it may blow up. Yeah, if it's 0.40, there's no value. Even if I take 1 as the upper bound, that's still not 95% of the interval. I don't know, we could play around with this for a while. All right, now we could also do the following. I could also find the lower bound such that the upper bound of the interval is 0.99. Okay? That is, this is a slightly different computation. And now what I want to do, in a little bit of complicated code here, is to find, basically, show a variety of possible intervals that comprise 95%. All right, and so, in fact, this is sort of what I was articulating before, that where that upper bound ends depends on the lower bound. And we actually only get to these higher values of the upper bound when we start putting the lower bound up at a value of 0.333. All right, so what I'm trying to show you is that one issue with credible intervals is that they're not unique. And so we need a theory to choose among the credible intervals. Okay? There are two approaches that are used for choosing among credible intervals, and because there's not one right answer, if you see someone using credible intervals, you ought to poke at them and find out what method they used for choosing it. And if they don't know, which is quite likely, then they're really not doing statistics. They're just sticking numbers into some formula and not know, or some computer, and really not knowing what they're doing. All right. So basically, what we're doing here is writing some code to find the narrowest credible interval. We're going to try and minimize the difference between the upper bound and the lower bound. Okay? So, as it turns out, it's minimized when the lower bound is 0.30 and the upper bound is 0.75. Another theory of how to do it is to use what's called the equal-tailed interval. The idea is we want to have as much of the probability distribution to the right of the upper bound of the credible interval as there is probability distribution to the left of the lower bound of the credible interval. And so we can do that here and do the computation. And what you're going to see is it's different, but it's not hugely different. And so it is true as a practical matter in some instances. It may not matter which method you use, but still, who's ever using Bayesian statistics ought to know what the heck that they are talking about. I'll let you read on your own the discussion on Stack Exchange about the difference between confidence intervals and credible intervals, but I do recommend that you read it, as I think it's a helpful way of understanding a difference between Bayesian statistics and conventional frequentist statistics. All right, so one of the things we discussed, or I've discussed, is how Bayes' law is basically a method for updating probability estimates. And so as you start with some prior, but the more evidence you get, the more your posterior should start to converge on the true value. And in some sense, the less important the prior might be. I now want to show you how the posterior evolves in light of new evidence. To do this, I'm afraid I'm going to need to use a little more complicated code than we've seen so far. If you work through it hard, I think you'll be able to follow it, but it's not going to be something that you're likely to get on first glance. We need an auxiliary function here that's going to determine basically the possible values a distribution can produce. And then we're going to write a function posterior that takes a prior distribution. This little thing here says on condition that it actually is a distribution. I'm going to find out where the draw distribution is coming from. In other words, the prior is the distribution of the parameter to the distribution from which the draw is being taken. And the final argument is a list of the values that we are observing. Okay? And so I've really just automated here what I did before. We're going to take the PDF of the prior, that's P of A in Bayes' law terms. I'm going to compute P of B given A in Bayes' law's terms. That is, I'm going to compute the product of basically the likelihood of each draw under a symbolic distribution from which I'm drawing, and that's going to give me a joint likelihood. I then need to normalize that joint likelihood as I did before. This is the integral part. I need to know what the bounds of the integral are. That's what this little code is about. And then I just want to do a little bit of algebraic simplification here by telling it, hey, p's got to be somewhere in the bounds of the prior. So that's the idea of the code. Let's make sure that's in the kernel. And now we'll just automate it. Remember that whole thing we did before? Here's our prior. Here's the family that we're pretty sure we're drawing from. And here's the evidence. And so we run that, and we get exactly what we did before. All right. Now let's just up the level of complexity a little bit here. And we're going to use random variate to generate a sequence of 50 zeros and ones. Now, in the real world, I would not know that this was coming from a Bernoulli distribution with a parameter of 0.3. All I would see was this. And you know, I feel I should seed my random number generator so that this doesn't change every time we use it. And we'll just use that as our seed. All right, great. Let's run it. There's our values. And now what I want to do is to compute the posterior distribution just based on one piece of evidence, then based on 2 pieces of evidence, 3 pieces of evidence, 4 pieces of evidence. And so we're going to be taking from this value I numbers as I goes from 1 to 50 and computing the posterior distribution. And so this is going to give us a table of PDFs. And it may take a few moments. All right, there we are. And now what we can do is to see visually how those PDFs are going to evolve as the data comes in. And so you can see, here's our original data, where we had a belief that it was like this, but now we've got data, more data is coming in, and this is kind of where we end up, which is basically saying, look, I'm pretty darn sure this is someplace between about 0.25 and 0.35. So just to convince yourself that this is correct, or that it will converge, here I'm going to start with a different prior, beta 4.5. We'll compute the same sequence here. And now let's look at what the evolving posterior distribution looks like. And you can see that, again, we start out from a different place, but we end up in a pretty similar place. So this is the idea that for small amounts of data, prior matters a lot. The more data we get, we're going to really be relying on that data more so than our prior to figure out the distribution of the parameter to the underlying distribution. So that is it for Bayes' law for today. And for a while, you should really memorize this formula, and you should probably more importantly, you should understand it. So if you don't remember it, you can recompute it. I also think understanding the Sanderson formula, Grant Sanderson's formula, is useful, and being able to go back and forth between odds and probability is a good idea. Thanks for your attention, and enjoy Bayesian statistics.